124 light-years from Earth, there is a planet shrouded in mist and mystery. The James Webb Space Telescope has found something in its skies, a chemical whisper that, on Earth, only living things produce. This world is not just another exoplanet. It might be the first true Hycean world, and it could be alive. Chapter 1. Discovery and Distance. 124 light-years away, in the quiet stretch of sky within the constellation Leo, there is a world we cannot yet see with our own eyes. It is called K2-18b. To most people, that name sounds like a string of letters and numbers, but to astronomers, it represents one of the most intriguing finds of the last decade. The planet was first noticed in 2015 by NASA's Kepler Space Telescope during its K2 mission. At the time, it was just another data point among thousands, one of many dim dips in a star-esque light that hinted at a hidden companion passing in front of it. The numbers said it was bigger than Earth, about 2.6 times its radius, and it orbited a cool red dwarf star. That was interesting, but not enough to cause a stir. There were, after all, many such planets, but over time, K2-18b refused to fade into the background. Its location caught attention. It sits in the habitable zone of its star, the region where temperatures could allow liquid water to exist. For scientists searching for life, that is the first box to check. The next step was to understand its atmosphere, its composition, and its potential to host oceans or clouds. The James Webb Space Telescope changed everything. Unlike older telescopes, Webb can read the light filtering through a planet's atmosphere as it passes in front of its star. Each gas leaves a distinct fingerprint in that light, and in 2023, when Webb observed K2-18b, the fingerprints it found did not belong to ordinary, lifeless gases alone. Before we get there, imagine the scale of this journey. Light, the fastest thing in the universe, takes 124 years to travel from that world to us. If you could somehow get there in a spacecraft moving at the speed of the Voyager, probes currently the fastest human-made objects, you would still need millions of years to arrive. This is not a place we can visit anytime soon. We can only study the light it sends us. That faint, ancient light is all we have, yet it tells a story rich enough to change our understanding of life itself. When scientists talk about K2-18b, they often compare it to a super-Earth or a mini-Neptune. It's too big to be rocky like our planet, but smaller than the ice giants in our solar system. That means it might have a thick atmosphere and possibly a vast ocean beneath. This is where the mystery begins. Oceans mean water, and water means the possibility of life. But until recently, we had no way to confirm such details. K2-18b orbits a red dwarf star called K2-18. Red dwarfs are smaller and cooler than the Sun, but they burn for trillions of years, far longer than our own star will. That means planets around them could have stable environments for immense spans of time. But red dwarfs can also flare violently, sending out bursts of radiation. For life to survive, a planet's atmosphere must be thick enough to shield it from these storms. Whether K2-18b has such protection is one of the key questions astronomers are trying to answer. The more we learned, the more it seemed that K2-18b was not just a random planet in a dataset. Its size, position, and potential ocean made it a prime candidate for a type of world we have only begun to imagine, a Hycean world, a term that blends hydrogen and ocean. This concept describes planets with vast water coverage and atmospheres rich in hydrogen. Theorists believe such worlds could be abundant in our galaxy and could host life in environments very different from Earth. In the early days of exoplanet science, the focus was on finding Earth twins, planets of the same size and temperature as our own. But K2-18b reminds us that life might not need an Earth copy to thrive. It might emerge on worlds that are bigger, wetter, and stranger than anything we have here. And that possibility has pushed this planet into the spotlight. To understand K2-18b is to stretch your imagination. Picture a world bathed in the soft red glow of its star, with no countenance in sight. Only endless ocean stretching under a hazy, pale sky. Somewhere beneath that sky, winds sweep across alien waves, and the chemistry of life, perhaps not life as we know it, is at work. We do not know yet, but every new observation takes us closer to finding out. The story of K2-18b is still being written. In the chapters ahead, we will explore what makes a Hycean world unique, the chemical signals detected in its atmosphere, the meaning of those signals, and what comes next in our search for life beyond Earth. But it all starts here, with a faint flicker of light in the constellation Leo, carrying whispers from a distant ocean world. Chapter 2. What makes a Hycean world? A Hycean world is an ocean planet with a hydrogen-rich atmosphere. That short line carries a lot of meaning. It tells us about air, water, heat, light, and the possible homes where life could exist beyond Earth. In this chapter, we will unpack that idea step by step, in clear terms, so you can picture the place, and understand why scientists are excited about it and why K2-18b may be our first strong example. Let's start with the air. On Earth, our air is mostly nitrogen and oxygen. On a Hycean planet, the air is very different. It is dominated by hydrogen, often mixed with helium and small amounts of other gases like water vapor, methane, and carbon dioxide. Hydrogen is the lightest gas, and that matters. A light gas gives an atmosphere a large-scale height, which is a technical way of saying the atmosphere puffs up more. When a planet with a puffy, hydrogen-rich atmosphere passes in front of its star, starlight filters through many kilometers of gas. That makes it easier for our telescopes to read the chemical fingerprints in that light. For this reason, Hycean planets are not only interesting, they are observable. We can study them now, with tools like the James Webb Space Telescope. Now the water. The scene in Hycean points to ocean. These worlds may have global oceans that wrap the planet from pole to pole. There might be no continents, no dry land, only water and clouds. Imagine standing at the edge of an endless sea, but on a world where the sky is a pale, hazy blue-gray and the sunlight is redder because it comes from a small, cool star. The waves might move under thick mists, fed by constant evaporation. Rain could fall in slow curtains and vanish into fog again. It is a quiet, heavy scene and it might be one of the best places to look for life. But can a planet like that really be habitable? Yes. In theory, a hydrogen-rich atmosphere can trap heat efficiently, a bit like a blanket. If the planet is in the habitable zone of its star, the region where liquid water can exist, its thick air can smooth out temperature swings and keep surface waters mild, not too hot, not too cold. This is key. Habitability is not only about distance to the star, it's also about the atmosphere. A Hycean atmosphere can turn a wide range of orbits into stable, ocean-friendly climates. Still, oceans bring new questions. How deep are they? Many models suggest Hycean oceans could be very deep, perhaps hundreds of kilometers. At great depths, water turns into high-pressure ices, like Ice 6 or Ice 7, even if the surface is liquid. That means the seafloor might not be rocky in the way we know it on Earth. There could be a layer of high-pressure ice between the water and the rock below. If that is true, life would likely prefer the upper ocean, where water meets the atmosphere and sunlight, if any, can reach. Life there could feed on chemical energy as well as light, using reactions between gases in the air and molecules dissolved in the sea. Let's talk about the star. Many Hycean candidates orbit red dwarfs, also called M-dwarfs. These stars are small, cool and long-lived. They can shine for trillions of years. A planet around such a star often orbits close in, which means it may be tidally locked. One side always faces the star endless day, and the other is in constant night. That sounds extreme, but a thick hydrogen atmosphere and a global ocean can move heat from the day side to the night side. Winds and currents can prevent the day side from boiling and the night side from freezing. The result could be a large band of temperate conditions around the terminator, the line between day and night, or even global mildness if the circulation is strong. Again, the atmosphere is the hero. There are risks. Red dwarfs can have stellar flares that blast planets with radiation. If the atmosphere is thin, life suffers. But a dense hydrogen envelope can shield the surface, and clouds can reflect dangerous light. Some Hycean worlds might also have magnetic fields that help deflect charged particles. We do not know each planet's protection yet, but these defenses are possible, and that keeps Hycean habitability on the table. Why are scientists focusing on these worlds now? There are two big reasons. First, they appear to be common. When astronomers count planets in other systems, they see a huge population between Earth and Neptune in size, often called super-Earths and mini-Neptunes. We do not have that type in our own solar system, so they feel alien, but elsewhere they are everywhere. Many of these worlds could have deep oceans and hydrogen-rich air. If you want to find life beyond Earth, it makes sense to look where the planets are common. Second, Hycean atmospheres make spectroscopies, the reading of chemical fingerprints, much easier. On a rocky Earth-sized world with a thin atmosphere, the signal is faint and difficult to detect. On a Hycean world, the signal can be strong. That means we can search for biosignature gases linked to life today, not decades from now. We can check for patterns like methane paired with carbon dioxide in certain ratios, or other combinations that are hard to explain without biological activity. This is a practical advantage that Hycean worlds have over true Earth twins. Let's build a simple mental picture of a generic Hycean planet. It is about 2 to 3 times Earth's radius and maybe 8 to 10 times Earth's mass, though values can vary. It likely has a rocky core, a very thick water layer, and a hydrogen-helium atmosphere on top. The sky holds cloud decks at different heights. Sunlight redder and softer than ours filters through haze and meets the ocean in scattered beams. At the surface, temperatures can be in a liquid water range. The air carries water vapor and trace gases that shift with weather patterns, and those shifts change the spectrum we see from far away. Over time, with repeated observations, we can tell which gases are stable parts of the air, and which are seasonal or weather-driven. That is how we turn spectrums into stories about climate. What about nutrients? On Earth, life in the ocean depends on elements like nitrogen, phosphorus, and iron. In a deep global ocean, the cycling of nutrients might be different. There may be upwelling currents that bring minerals from the deep to the surface. There may be atmospheric deposition of dust or aerosols that supply key elements. There might be hydrothermal activity at the base of the ocean, even if a high-pressure ice layer separates water from rock. Cracks, mixing zones, or long-term seepage could still deliver chemistry. We cannot see those details yet, but the possibility is enough to keep Hycean worlds high on the target list. Clouds matter too. Thick clouds can hide the lower atmosphere from our view, but they also stabilize climate by reflecting starlight and trapping heat. In the best cases, clouds form a self-regulating layer. They grow when it's warm, reflecting more light, and cooling the planet. They thin when it's cool, letting in more light and warming it again. This kind of feedback can hold a Hycean world in a Goldilocks state for long periods. Now, where does K2-18b fit? Based on its size, mass, and the region it orbits, K2-18b is a prime Hycean candidate. It sits in the habitable zone of a red dwarf star. It is bigger than Earth, so a hydrogen-rich atmosphere is plausible. Recent observations suggest water-friendly conditions in the air and the potential for a large, warm ocean below. We do not claim certainty. We claim consistency with the Hycean idea. That is powerful, because consistency is what we look for first. Does the data match the picture? With K2-18b, many pieces line up. There are still open questions. How thick is the atmosphere? How much ultraviolet radiation hits the surface? Does the planet keep a stable climate over long timescales, or does it swing between hot and cold states? If the world is tidally locked, is the day side covered by permanent clouds that reflect light and keep temperatures steady? Is there a terminator ring a belt around the twilight zone, where conditions are best? These questions guide the next observations. They help us choose which parts of the atmosphere to probe and which gases to measure with the highest precision. Another point matters for life: chemistry at the ocean-atmosphere boundary. On Earth, this boundary is rich with interactions, waves, spray, foams, and films where gases dissolve into water and new molecules form. On a Hycean world, that boundary could be a factory for complex chemistry. Hydrogen in the air can meet carbon-bearing gases and water vapor to build more complicated molecules. Sunlight and lightning can provide energy for reactions. Over time, this chemistry could create organic compounds that act as building blocks for life. If life does take hold, it may leave traces in the air patterns of gases that are hard to explain by geology or sunlight alone. We should also face the challenges. A thick hydrogen atmosphere can escape into space over billions of years, especially if the star is active. The planet's gravity must be strong enough to hold the gas. Stellar winds and flares can strip the upper layers. The ocean could become too hot if the greenhouse effect runs away, or it could freeze if clouds reflect too much light. These risks are real, but they do not erase the opportunity. They simply mean we need better measurements and careful models. This is why Hycean worlds are a step change in the search for life. They expand our idea of habitability beyond Earth clones. They offer signals we can detect with today's instruments, and they are likely common, which raises the odds that at least some of them host stable, life-friendly environments. If you were designing a strategy to find life in the near term, you would put Hycean planets near the top of the list. Picture K2-18b one more time. A red sun rises over a wide, warm ocean. The sky is layered with thin, high clouds and thicker decks below. The air is light, buoyant, and full of water vapor. Gentle winds move heat from the bright hemisphere to the dark one, keeping the planet comfortable along a broad band. At the surface, tiny droplets form, burst, and reform in a constant cycle. Chemistry never stops. If life has a foothold, it may live here at the skin of the sea, where the air meets water, where light still has power. In the next chapter, we will look for evidence. We will talk about the chemical signals that telescopes have started to see in K2-18b's atmosphere, how those signals are measured, what they might mean, and how we can tell natural processes from the possible breath of life. For now, remember the core idea. A Hycean world is an ocean planet wrapped in hydrogen. It is a new kind of home for life, and it might be the most promising one we can actually study today. Chapter 3. The Chemical Signal, the James Webb Space Telescope. Humanity's most powerful eye in the cosmos was not built merely to take pictures. It was built to read the light of alien worlds. And when scientists turned its gaze toward K2-18b, a planet orbiting a dim red dwarf star 120 light-years from Earth, they weren't looking for mountains or oceans. They were listening for chemical whispers, signals carried in the thin veil of gases surrounding the planet. JWST used a method called transmission spectroscopy, a technique that turns starlight into a cosmic fingerprint. Here's how it works. When K2-18b passes in front of its star, a small fraction of the starlight filters through its atmosphere before reaching us. Certain molecules absorb very specific wavelengths of that light, creating tiny dips in the spectrum, like missing musical notes in a song. By studying those patterns, astronomers can determine which gases are present, even from unimaginably far away. When the Webb team examined K2-18b's spectral data, they found something that made their hearts race. Dimethyl sulfide, or DM. On Earth, DMs has a unique origin. It is almost entirely produced by living organisms, particularly microscopic marine phytoplankton. These plankton drift in the oceans, turning sunlight into energy, and when they die or are eaten, they release DMs into the atmosphere. It is a key part of our planet's sulfur cycle, and even plays a role in cloud formation. In fact, the faint salty scent you smell at the seaside, the one that feels almost alive, is often the smell of DMs drifting in from the ocean. What makes this discovery remarkable is that, as far as we know, no purely geological or abiotic process on Earth produces DMs in large quantities. Volcanoes, hydrothermal vents, and chemical reactions in the atmosphere simply can't account for it. This means that here, at least DMs is a chemical signature of life. So to detect it on a planet so far away immediately raises a staggering question. Could something alive be exhaling this gas on K2-18b? But scientists are careful by nature. While the Webb data shows a 99.7% probability that the signal is real, they know that extraordinary claims require extraordinary evidence. That number 99.7% in most other sciences would be considered a slam dunk. In particle physics, it's on the edge of what's called 3 sigma confidence. Yet in the search for extraterrestrial life, the bar is set even higher. Researchers must consider every possible alternative explanation. Could there be some exotic chemical reaction in a Hycean world's atmosphere that creates DMs without biology? Could a volcanic plume, under extreme pressures and temperatures, mimic this signature? Could even the telescope's own instruments have introduced an artifact? Each possibility must be tested, dismantled, and ruled out. And DMs was not the only gas in the story. The Webb telescope also detected methane and carbon dioxide gases that, in combination, can be highly suggestive. On our own planet, methane often comes from biological sources, though it can also emerge from geological activity. Carbon dioxide is a common atmospheric gas produced by volcanoes, respiration, and chemical weathering. But together, in the proportions detected on K2-18b, they paint a picture that is hard to ignore. A world where carbon-based chemistry is active, and possibly one with liquid oceans beneath a thick, protective atmosphere. K2-18b is thought to be a Hycean worlder type of planet covered in a global ocean, with a hydrogen-rich atmosphere and conditions that could be stable for billions of years. If that's true, then methane, carbon dioxide, and DMs together might indicate an environment, much like Earth's early seas, teeming with microbial life, long before the first forests or continents appeared. The detection doesn't just hint at habitability, hints at activity. But here's the catch. Our instruments are reading this from 120 light-years away. That's over 1 trillion kilometers times a millionaire scale, so vast that even light, the fastest thing in the universe, takes more than a century to make the trip. The photons carrying this data left K2-18b when the world was still recovering from the First World War. We are, quite literally, studying ancient history every time we analyze these signals. The distance also means that confirming life will be incredibly difficult. We cannot yet send a probe. We cannot yet take a direct image of its surface. All we have is the starlight filtered, scattered, and faint, and the skill to read its code. It's like trying to learn about a distant city by studying the pattern of its streetlights through a telescope. Still, even with these limitations, the DM signal is unlike anything astronomers have seen before. For decades, scientists have searched exoplanet atmospheres for biosignatures, oxygen, ozone, methane, in certain contexts, but always with caveats. Many of those gases can be produced without life. DMs is different. If the detection is confirmed, it will be the first time we've found a molecule that, on Earth, is only made by living organisms. And yet, the scientists involved in the discovery are careful not to declare victory. They speak in cautious tones, aware of the weight of such an announcement. False positives have plagued the search for life before, like the controversial claims of methane on Mars, or the debated fossil-like structures in a Martian meteorite in the 1990s. Each time, initial excitement gave way to more complicated explanations. That's why the Webb team emphasizes, this is not proof. This is a clue. A strong, tantalizing clue. But for those who have been following the search for life beyond Earth, this moment feels different. Because if you strip away the scientific caution and look at the raw facts, what we know about DMS, how it's produced, and the environment of K2-18b, you are left with something that, for now, is the loudest whisper the cosmos has given us. Imagine standing on a windswept shore of that distant ocean world. Above you, the red glow of its parent star filters through clouds. Somewhere in the waves, microscopic organisms drift, unseen, but their presence is betrayed by the molecules they release, molecules that travel upward, scatter through the air, and eventually leave the planet altogether, carried across the vacuum of space until, after 120 years, they reach our waiting telescope. It's humbling, it's breathtaking, and it changes the way we see our place in the universe. It's not proof, but it might be the first time another world has leaned in and whispered, "We are here." Chapter 4. Implications for the search for life. The detection of potential biosignatures on K2-18b is more than just a scientific milestone, it's a philosophical jolt. If the hints of life are real, this small distant world could be a quiet confirmation that we have never truly been alone. It would mean that the conditions necessary for life are not unique to Earth. They might not even be rare. Instead, life could be an inevitable outcome when certain planetary recipes come together. scattered across the galaxy like seeds on the wind. For decades, our search for life has been defined by Earth's example. We looked for twin worlds with blue skies, green continents, and climates that mirror our own. But K2-18b challenges that comfort zone. It is not an Earth twin. It is larger, heavier, and cloaked in a thick atmosphere of hydrogen. Its oceans, if they exist, are hidden beneath alien clouds. It is, by every traditional measure, strange, and yet, it may be alive. This is the kind of revelation that forces scientists to rewrite their models of habitability. Until recently, habitable meant Earth-like. Now, the category must stretch to include Hycean worlds, planets with hydrogen-rich atmospheres and global oceans, potentially capable of supporting life forms that evolved under conditions we once thought were hostile. If K2-18b proves to be inhabited, it suggests that life is adaptable beyond our imagination. It could thrive in chemical soups far different from the ones that nurtured Earth's microbes. It could breathe gases we would find toxic, feast on energy sources we've never considered, and flourish in darkness beneath alien seas. Imagine the implications for our search strategy. If life can exist in such exotic conditions, then the number of potential life-hosting worlds multiplies. Instead of focusing only on rocky planets in narrow Goldilocks zones, astronomers might prioritize a much wider variety of candidates worlds, with dense atmospheres, subsurface oceans, or even planets orbiting dim, cool stars. Our map of possible homes for life would expand overnight. It's also a reminder of our own planet's deep history. Long before Earth had continents, forests, or mammals, life thrived in its oceans. For billions of years, microscopic organisms were the sole inhabitants of our world. They needed no land, no oxygen-rich sky, no sunlight reaching every corner. They were proof that life doesn't need perfection, it needs opportunity. K2-18b may be a living echo of that early Earth, a water-rich cradle where life could emerge without the familiar comforts we take for granted. And here's the truly humbling part. If life can arise on such a world, it probably has done so countless times in the galaxy's history. The Milky Way alone holds hundreds of billions of stars. Even if only a fraction of them have planets, and only a fraction of those planets have oceans, the numbers still soar into the millions of possible habitats. That means that our cosmic neighborhood may be far busier than we dare to imagine. But there is also a philosophical shift hidden in this discovery. For centuries, humanity has been looking for reflections of itself, worlds that resemble our own, civilizations that might think as we do. But perhaps the universe does not offer us mirrors. Perhaps it offers strangers. Life on K2-18b, if it exists, may not look like anything we know. It may not communicate, build, or dream as we do. It could be as alien to us as our earliest microbes would be to a human today. And yet, in its own way, it would still be our cosmic quinner, fellow passenger on the great voyage of existence. This change in thinking also affects how we interpret silence. The so-called great silence of the universe, the absence of clear signals from other civilizations, may not mean we are alone. It may mean that most life is microbial, thriving quietly in oceans and atmospheres far from the reach of radio telescopes. Intelligent life could be rare, but living worlds could be common. The more we discover about exoplanets like K2-18b, the more this seems like a plausible reality. Scientists are now faced with a choice. Do we continue searching for civilizations like ours, broadcasting messages in the hope of an answer? Or do we focus on detecting the faint chemical whispers of alien biology, the gases, molecules, and patterns that life leaves behind, even when it cannot speak to us? K2-18b leans heavily toward the second path. It tells us that even without a handshake across the stars, we can still meet another form of life through science. The confirmation of life on such a world would also raise difficult questions about our place in the universe. If life is everywhere, what does that make us? Are we just one story among billions? Or is there something still rare about our journey from microbes to thinkers, from oceans to spaceflight? For some, the discovery might make life feel less unique. For others, it might make existence feel even more precious because it would mean that we are part of something vast, ancient, and shared. There's also the emotional weight of the discovery. Humanity has always been a storytelling species, and the idea of life beyond Earth has been woven into our myths, religions, and dreams for thousands of years, to finally glimpse it not in the form of a green-skinned visitor, but as a subtle chemical trace in the spectrum of a distant star would be a poetic twist. It's as a reminder that the truth of the universe may not arrive in the ways we expect. Sometimes it's not a knock at the door, but a faint whisper from light years away. Of course, we must remember the caution in science. Even if all signs point toward life, the burden of proof is immense. Extraordinary claims require extraordinary evidence. K2-18b's story is still being written, and the final chapter may yet surprise us. But whether this world is alive or not, it has already expanded the boundaries of our imagination. It has shown us that the search for life is not a straight path toward Earth's twin, but a sprawling journey through worlds stranger than fiction. Perhaps we have indeed been looking for mirrors of ourselves, while the universe holds strangers beyond imagination. And maybe, just maybe, those strangers are waiting for us to notice them, not with a shout, but with a silent shimmer in the starlight. Chapter 5, The Road Ahead. The discovery around K2-18b has left the scientific community at a crossroads. We are standing on the edge of something extraordinary, yet the path ahead is shrouded in uncertainty. Finding signs of life, or something that could be life, on a planet more than 120 light-years away is not the end of the story. In many ways, it's only the opening chapter. The next steps will test the limits of our technology, our patience, and perhaps our imagination. The James Webb Space Telescope has already given us unprecedented detail about K2-18b's atmosphere. But to truly understand what's happening on that distant Hycean world, we need more data, and much more time. Webb will continue to revisit K2-18b in the coming years, capturing new spectra under different orbital conditions, subtle changes in atmospheric composition, seasonal variations, and the detection of other trace molecules could strengthen or weaken the case for life. Every new observation will be like adding another brushstroke to an unfinished portrait. Beyond JWST, a new generation of telescopes is already on the drawing board. The Habitable Worlds Observatory, planned for the 2030s, is designed specifically to study Earth-sized planets in the habitable zones of their stars. With its advanced coronagraph technology, it could directly image worlds like K2-18b, separating the faint planetary light from the overwhelming glare of its star. If we are lucky, it might even detect patterns of light reflected from oceans, clouds, or vegetation-like surfaces. Combined with spectroscopy, that could bring us closer than ever to confirming biosignatures. On the ground, massive observatories like the extremely large telescope in Chile will complement space-based observations. Using adaptive optics and next-generation spectrographs, these facilities could analyze exoplanet atmospheres from Earth with incredible precision. While ground telescopes can't match the clarity of space-based instruments, they can conduct long-term monitoring, spotting trends and anomalies that space missions might miss. But confirming life from such a distance is a monumental challenge. Even if we detect multiple biosignatures, dimethyl sulfide, methane, carbon dioxide, and see them in combinations that on Earth point strongly toward biology, there will always be alternative explanations. Volcanism, photochemistry, and exotic non-biological processes could mimic life's chemical fingerprints. The scientific community is cautious for good reason. A false positive would be a devastating blow, not just to this discovery, but to the credibility of exoplanet research as a whole. That's why scientists are pushing for a multi-pronged approach. Instead of relying on a single gas as proof, they want to see a network of chemical clues, gases in disequilibrium, unusual temperature profiles, and patterns of variability that match biological cycles. The more lines of evidence we can gather, the stronger the case becomes. K2-18b offers a rare opportunity to test this method, because its size, atmosphere, and possible oceanic nature make it ideal for repeated, detailed observations. In the next decade, we may also see breakthroughs in interstellar communication and detection, not in the sense of talking to aliens that remains speculative, but in detecting energy signatures or technological markers, sometimes called technosignatures. If any advanced civilization existed on K2-18b, they might emit signals detectable by our radio telescopes, or leave other telltale signs. While the probability is extremely low, the search for technosignatures will run in parallel with biosignature hunting, ensuring we don't miss the unexpected. Yet, despite all these advances, we must remember the scale of the challenge. Light from K2-18b takes over a century to reach us. We cannot send a probe there in any reasonable time frame with current technology. All of our conclusions will rest on interpreting faint, filtered light. This is a humbling reminder. Even if we do find compelling evidence of life, it will exist as patterns in a graph, as peaks in a spectrum, as lines of data. The romance of imagining alien oceans and skies will have to be balanced with the reality that, for now, we cannot go there. Still, that doesn't diminish the wonder. If we find life, even microbial, on K2-18b, it would be the most profound discovery in human history. It would mean that life is not a miracle confined to one pale blue dot. It would mean that the universe is fertile, that biology is a natural outcome of chemistry, and that somewhere, in the darkness, countless other worlds may be alive. And so we continue to watch. The Webb telescope will pass the torch to the Habitable Worlds Observatory, to the next generation of instruments, and eventually to telescopes we haven't even imagined yet. Each will sharpen our vision, peeling away the layers of mystery. Perhaps one day, the data will leave no room for doubt. Until then, the search itself is a kind of reward. Every step we take toward understanding K2-18b teaches us more about the universe, and about ourselves. We learn patience, we learn humility, and we learn that the hunger to know is as much a part of us as the air we breathe. Somewhere, right now, under alien waves, something may be watching its own sky, not knowing we are watching back. Maybe it moves slowly through currents we cannot feel. Maybe it senses its world changing with the pull of its sun. Maybe, like us, it wonders if it is alone. If you want to follow the search for life beyond Earth, to stand on the edge of each new discovery with us, consider subscribing, sharing your thoughts in the comments, and joining this journey. Together, we can explore these mysteries, one distant world at a time. If you want to follow the search for life beyond Earth, consider subscribing, sharing your thoughts in the comments, and helping us explore these mysteries together.